I welcome you all to this lecture of microscale transport process. What we have been discussing so far is various microfabrication techniques. We have discussed how to fabricate, discussed about how to fabricate a channel on a silicon or glass wafer, and how to cover that channel with a lead using an anodic bonder or a fusion bonder. And also we discussed various techniques to fabricate plastic microfluidic devices, and we discussed about various advantages and disadvantages of these devices. So far what we have, and of course we have discussed about how to put a tubular, how to insert a capillary so that this microstructure device can be interfaced with the external world. So we pretty much we are already done with various microfabrication techniques. The last issue that I am left with as far as the microfabrication is concerned is biocompatibility. Many of these microfluidic devices, they will be used in they are supposed to be used in human body for various reasons, either to analyze, either to release drug at some point, or analyze the level of toxins, or due to various reasons it needs to be put to human body. So, the major part of the applications of microfluidic devices cover uses in human body. So, we need to understand some issues here, or at least the terms here that are important. Biocompatibility, we hear these terms so often. Okay, this material is biocompatible, that means if you insert in human body, you do not expect a adverse reaction. That is the immediate response that I will get if I ask you this question, what a biocompatibility would be. Now, the way this biocompatibility is defined here is in this slide. I write biocompatibility. There are 2 points here, one is called material response and the other is called cellular response. One is the response that is given by the material itself. That means, you insert a microstructure device inside human body. Now, that material will respond in certain way. I mean, you have to ensure that the material remains intact, the material does not erode or material does not swell. So, that is important. The other issue is the cellular response. The cells around that material, the human body, that should not get destroyed. So, there are 2 points here. One is that microstructure device should not get destroyed by human body, because human body itself contains a lot of chemicals, and if that microstructure device swells, ruptures, erodes, so if that does not function, then the purpose would be lost. That is one issue. The other issue is that the material that you insert in human body, that should not cause some adverse reaction, that the cells around that material gets destroyed, then you have some other problem. So, if we get back to this material response is generated by the device inside host tissue. Okay. So, this material response is generated by the device, not by the human body, it is by the device that you insert, and this is caused by diffusion of body fluid from host tissue into the device. Diffusion of body fluid, the body fluid is there and you have inserted this material inside the human body. So, this material is coming in contact with the body fluid. Now, if the body fluid diffuses into the human diffuses into this device, and then that device material swells, that is the third point I write here. Device material swells, develops micro cracks on the surface, altered mechanical properties, and in some cases leaching. So, these are the problems that would happen if the body fluid enters into the device, okay, and because of that the device material swells, it develops micro crack. Okay. Swelling involves, I mean, the moment it starts swelling, I mean, you don't know what is going to happen, because you are stretching it. Some place it is getting stretched, some place it is not. So, there would be stresses developed, and at any point there could be a crack developing. Okay. So, swelling is something which you have to be careful with. So, develops micro cracks on the surface, and it can have altered mechanical properties. If something swells, it has to have some kind of structural integrity, and that integrity would be lost. So, that is a problem with the material, and in some cases there could be leaching. That means, the body fluid may leach out some essential part of that device. Okay. Suppose on the device you have some coating, okay, and the body fluid starts leaching. You know what a leaching is. So far you have in various chemical engineering applications, you understand what a leaching process is. If you have not, I suggest you read any mass transfer book by say mass transfer by Coulson Richardson or mass transfer by Treball. You can pick up any of these books in the library, and then you can read this chapter leaching. It is like this body fluid will take away some material from the surface of that microstructure device. So, then if such leaching happens, then the microstructure device will lose its structural integrity, it will lose its ability to perform inside human body. So, these are not wanted basically. So, this is what I refer as material response. So, this is as far as the device part is concerned. The other part is the cellular response. Once you put the device, you have to ensure that the cells around it should not get destroyed. The body cells that are around this device, that should not get destroyed. So, this cellular response, this is generated by the host tissue. All right. So, this is generated by the host tissue. Inflammation at the device tissue interface. So, moment you put this microstructure device, there would be inflammation at the device tissue interface. Okay. This will cause reddening and pain. If the inflammation lasts long and damages local cells, that is referred as, then the device is called cytotoxic. Okay. One thing I would like to point out at this point here is that moment you insert a material, external material in human body, there will be inflammation, there will be reddening, there will be pain. So, these are few things which will happen invariably, and if these things happen, that does not necessarily mean that the body is that microstructure device is not biocompatible. You cannot say that, because anything you put, this will invariably happen. But what is important here is whether that thing dies down or not, whether the inflammation is, after some time the inflammation goes away, after some time the pain goes away, then only you will take that material as biocompatible. It is as straight as this. All right. So, inflammation at the device tissue interface, that will happen invariably whether it is biocompatible or not biocompatible. Okay. These reddening and pain, all these things will happen, but this will not last long. That is the indication of a biocompatible material. If it lasts long and damages, it starts damaging local cells, then the material is not biocompatible. Then the material is referred as then the device is referred as cytotoxic. All right. On the other hand, chemical signals released by the damaged tissue attract white blood cells. Typically, if you put a material which is supposed to be biocompatible, what will happen is immediately there would be inflammation, because moment you put an external material inside human body, the body will react in certain way. Okay. That is a must. If it does not happen, then it is not doing its job. So, the moment this happens, moment you insert a material inside human body, then there would be chemical signals released by the damaged tissue. Some tissue will be damaged, otherwise you cannot, because it is an integrated, it is an intact tissue. Inside that, when moment you are putting a material, that means you are damaging some tissue, some portion you are cutting out. So, those damaged tissues, they will release some chemical signals, and that chemical signal will ensure that white blood cells get attracted to that place. Okay. Basically, it is a human body send that portion of the body sends SOS to the rest of the body, that boy, there is a problem here. So, immediately there would be signals and blood cells, these white blood cells getting attracted, and in due course a fibrous encapsulation made of foreign body giant cell and macrophages is formed around the device. That means, these white blood cells that get attracted, it forms a fibrous encapsulation made of foreign body giant cells and macrophages. This is formed around the device. So, if this fibrous encapsulation forms, that means you are still okay, you do not have a problem. The material is not destroying the cells, rather what it has done is the portion, the tissue that you have damaged intentionally when you put the device inside, those tissues, they sent a signal and attracted white blood cells, which forms an encapsulation around the material. So, that part is okay, still the material can be biocompatible. As a matter of fact, I mean, I heard people who has I heard of people who have a bullet inside the body and they are leaving, they are just they said that okay, it is too troublesome here to operate and take out the bullet. So, let it be there. So, let it be there means it has already formed a fibrous, there is a fibrous encapsulation around that bullet and it is just safe. I mean, there is no more fallout of that injury. So, that is what I am referring to here. A fibrous encapsulation made of foreign body giant cells and macrophages is formed around the device. Now, one problem could be that this encapsulation that you have, these encapsulation may not allow the device to function properly. That means, suppose it is this device is a controlled release device. Controlled release device means when you want, it will release some drug at a specific location, and when you do not want, the drug will not be released. All right. So, that is the purpose of the device. Suppose the device that you have inserted. Now, if you have a encapsulation made and that encapsulation does not allow the material to release the drug, I mean, drug is released, but it cannot permeate through that encapsulation, then the purpose is lost, right. So, if the encapsulation does not affect, that is the point I have here, if the encapsulation does not affect the functioning of the device, okay, then you call it biocompatible. I wrote it in uppercase here in the slide, that then this is called, then this encapsulation, then this device is called biocompatible. So, you have so many checks. First of all, it should not be cytotoxic. First point, if it starts destroying the cells, no way, you cannot take it, that is cytotoxic. So, it is left out. Then it may come that it is not destroying, but it is forming a fibrous encapsulation, and that is disturbing the performance of that device. Then again you have a problem, but if that does not, even that does not happen, then you can consider this material to be biocompatible. All right. So, this is how you define biocompatibility. I mean in simple terms. Maybe there are other issues involved, but as far as this course is concerned, I thought these 2 slides on biocompatibility would be important. At least you have this in mind, that anything that if that is inserted in human body and it starts inflammation or pain, that does not mean that the material is not biocompatible. It could be that it is just simply biocompatible, because any material you insert in human body, this will end up with inflammation, pain, reddening and all this, but this should subside, this should not continue for long. Now, there are various tests done to check whether the material is biocompatible or not. There are 2 types of tests. One is called in vitro test. In vitro, you know the origin of this word vitro. Okay. So, in vitro means in laboratory glassware, and in vivo, that means in live animal or human. So, first suppose you have you can probably do some kind of screening by in vitro test, and then once you have identified, once you have shortlisted a few items, okay, these are the items I can consider them to be biocompatible, then you can run it on some animals whom you can sacrifice, for example, rat. Okay. So, that is one, that is how it is done, and once you know that it is not going to affect at least some animal body, then you will go for human trial. So, these are the ways biocompatibility is tested. So, this is one important issue, biocompatibility, and these microstructured devices, they are very often used in human body for various reasons. One could be really controlled release of drug, other could be, say there could be a glucose monitor placed inside the human body. It is continuously, it is measuring the level of if the patient is diabetic, it can continuously monitor his health. So, there could be such devices inserted into human body. So, these are basically some sensors which would sense how the body is performing, or it could be the material which can release drugs in a controlled manner, or it could be simply a mechanical it gives some mechanical action like a pacemaker or materials like this. So, these are the issues of biocompatibility that we must know as far as this course is concerned. Now, this ends the discussion on microfabrication. What I would do is I will probably come back to this later if any such problem comes up, if we need to revisit this microfabrication issues. What I want to get in now is basically the theories of microfabricated devices. I mean the transport processes, which our original intent was to study the transport process in microscale, and that now we are getting into this. But I thought this background of how this microfabrication is done will give you a very good idea about how things are done in practice. Okay, instead, I mean you can always do it in theories, but first you know where the limitations are as far as implementing things in practice. Then probably your understanding would be much better. I mean what we do with the theories. Now, when it comes to the theories, what I would like to introduce first is one thing you have to keep in mind, that suppose the dimension of a micro channel is say 100 micrometer, okay, and you have mu by rho. This is say I should write say channel is somewhere close to 100 micrometer, and mu by rho is close to 10 to the power minus 5 cm square per second. I mean you can check what is the viscosity of a common material that you have, what is the density you have, and you will see probably we come here, mu by rho is around 10 to the power minus 5 cm square per second. And then if we consider a velocity of 1 centimeter per second, 1 centimeter per second, I mean which is reasonable. I mean think of we are talking about a microstructure device which you are going to insert in human body. So, velocity of 1 centimeter per second would be considered pretty high in that respect, right. 1 centimeter per second we are talking about. So, if we use these parameters, and if somebody checks what is the Reynolds number, you will find that even with a higher level of velocity, your Reynolds number comes close to 1. And Reynolds number close to 1, I mean I have studied fluid mechanics, we talk about 2000 is the transition. So, Reynolds number of 1 is practically at the lower end of laminar flow. Even I mean you can say laminar flow even at the lower end of laminar flow. So, that is where we are operating when it comes to the flow in a microstructure device. So, when you remember in earlier classes we talked about these field flow fractionation, and we are using the concept of laminar flow, one layer sliding against the other, and then diffusion is taking place from one layer to the other. These, I mean we know for sure that we are nowhere close to the turbulence. We know for sure that the one layer is moving and the other layer is gently sliding against the other, because we are really at the low end of laminar flow. So, that is one thing you need to keep in mind, that generally we operate around this Reynolds number 2, 10, not more than that. Okay. The other point here is that you have this diffusivity. Diffusivity is of the order of, or diffusivity can be defined as penetration of a species divide the distance by which a species penetrates, square of that divided by the time it takes for the species to go up to that distance. Okay, that is how we commonly understand diffusivity or diffusion coefficient. All right, the distance that it has penetrated, because look at the unit of diffusivity, it is cm square per second. So this is typically what we understand about the diffusivity. A molecule diffusing means it will penetrate up to a distance delta x in time t, then delta x square by t is typically the diffusion coefficient. Now if that is so, then you can write, suppose I have a channel, I have a certain length of a channel. Okay, suppose I have a channel, I have half of it is a solute stream going in and half of it is a stream which does not have a solute, and they are flowing side by side. Okay, and I expect them to mix. I expect them to mix when it comes out. If one layer is flowing against the other, if one layer is sliding against the other, then you can expect that there would be diffusion taking place from one layer to the other. So if one stream has the solute, that means solute means I am talking about say salt solution. If you have a salt solution and if you have pure water and if you put them together side by side, you expect salt to go into the other stream which is pure water, and when you extract, when you take the entire solution at the outlet, you should expect that the entire stream would be well mixed. That means the portion which was pure water is now salty. Okay, so that is the diffusion we are referring to. Now if we expect that over the length L, if the length of this channel is L, okay, the dimension of this channel is say h, if the half width of this channel is h, say if the half width of this channel is h, okay, and you have the velocity as u, in that case you can expect, just think about the diffusivity. What is the diffusivity you have? 10 to the power minus 5 cm square per second. That is the typical diffusion coefficient you have for a common say NaCl solution. If you have, then that is the common diffusivity. Now if you put this diffusivity and if you expect this delta x, that is the penetration. Now that it has to penetrate the entire half width, right, at the end of the channel, then only you can consider them to be well mixed. Okay. So if that has to happen, what should be the length? Because you can write T as, so this T can be written as L by U, right. That is the time taken for this fluid to reach the outlet. Okay, so that is the time taken for the fluid to reach this outlet, and at the outlet the penetration should be complete. That means this delta x square should be replaced by h square. If you use these parameters, what you will find is that now the diffusivity can be, say I am assuming 10 to the power minus 5 cm square per second, it could go all the way up to 10 to the power minus 7 cm square per second if we are talking about diffusion of hemoglobin instead of sodium chloride solution. I mean sodium chloride is just a hypothetical one, nobody will mix water and NaCl in a microstructured device. Now one can mix hemoglobin, that he can do. So if we are talking about diffusion of hemoglobin, we are getting into 10 to the power minus 7 cm square per second. So if this is the range of diffusivity I have to cover, and if somebody asks you what should be the length of this channel, if this is the fact, this h, you know, the typical dimension of a microchannel is 100 micrometer. So what would be the length we are talking about here? And you will find that this length varies from 10 centimeter to 1000 centimeter. If this is the range of diffusivity that has to be covered. So it seems this diffusion is not is a slow process. I mean it will take. So if you expect two streams flowing side by side and it will have complete mixing at the outlet, the length of the channel should be 10 to 1000 centimeter. 1000 centimeter means we are talking about 10 meter. But typically human height is 1.6, 1.7 meter. So, 10 meter, I mean we are talking about that kind of length. So, we are not in definitely in a this is not a microstructured device. So, you cannot accomplish such level of mixing using two streams flowing side by side and relying entirely on diffusion. So, you have to have some other mechanism going on which by which what you do is you increase the interfacial area. That means, the two streams they are flowing side by side. If you introduce so called say probably in layman's term it would be baffles. If you introduce baffles by which you introduce extra area, interfacial area over which the mass exchange can take place, then probably you do not need such a long channel. So, my point, I mean why I introduce this diffusivity here, I mean the two issues that I point out here. First of all, the Reynolds number is really small in this case, we have already pointed out it would be around 1, and second point is that if it comes to mixing of two streams in a channel, you cannot expect them to flow side by side and get mixed. You have to introduce some baffles or some other method to arrange the mixing, and that some other method is introducing baffles, introducing some amount of chaos in this mixing process. Okay. So, but you got to understand here is by putting baffles, when we put baffles, one idea of putting baffles is to create some amount of turbulence. Okay, so that around the baffles there would be eddies forming. I mean in a conventional sense, in a pipe when you put baffles, you will make you will start having eddies. Eddies means packets of fluid flowing from one end to the other, which is in transverse direction to the actual principal flow direction. So, these are and that is associated with turbulence. Okay, and in this microfluidic device we are nowhere close to turbulence, we are in the low end of laminar flow. So, by putting baffles, the idea here is to create additional interfacial area. Okay, that the two streams, one is the solute stream, another is the solvent stream, they should have larger area for mass exchange. Okay. So, for that you introduce baffles. So, the purpose is little different. We will discuss this. We will put the theories of what is we call this a chaotic mixing. This mix by putting baffles and arranging a mixing. This mixing is referred as chaotic mixing. Now, this chaos is different from the chaos that is referred in context of turbulence, because nowhere it is turbulence, but this chaos is some I mean we will get into the theories of it probably by the end of this class or maybe in the next class. There is third issue. There are three issues I would like to point out. One is the issue of Reynolds number, I said. Another issue is the length, that if you rely on diffusivity alone, then it would be a very long channel which we cannot afford. The third issue is there is something called a Knudsen number. Knudsen number, which is defined as lambda divided by dH. And what is lambda? Lambda is the mean free path of the molecule, which can be written as kBT divided by square root of 2 pi sigma m square p, and this whole thing divided by dH. dH is, I mean, hydraulic diameter you can say, or some characteristic dimension of the channel. Okay. So, one is the mean free path and the other is the hydraulic diameter. Okay. Now, for now what are the various terms I have here, Kb, T, etc. I mean, you know what that is. Kb is basically Boltzmann constant, the value would be 1.38066 into 10 to the power minus 23 joule per K. T is temperature in absolute scale, then you have P, which is pressure, and you have sigma m, which is molecular diameter of the diffusing species. Okay. And I said dH is the hydraulic diameter. Now, if you look at the values of this lambda, if you look at the values of this lambda in case of a gas and in case of a liquid, for liquid it is of the level of angstrom, and this is of the level of micrometer for gases. Okay. So, what do we conclude from here? If you have lambda as lambda in the order of angstrom and lambda is of the order of micrometer in case of gases, then the Knudsen number would be important for which material? It would be for the gases. For the gases, the Knudsen number would be important. I mean, see, we are talking about this dH. If the Knudsen number will be important for liquids, Knudsen number will be important for liquids if the dH is of the order of nanometer. For liquids, if the dH is of the order of nanometer, then you can consider the Knudsen number to be important. Okay, but that is not probably, that does not come under the purview of this microscale process. Possibly if you are working with a separation process where you are separating some molecules within the liquid, then probably you would be working with that kind of range. But for a microstructure device, I mean, we at the very outset we said the channel dimension is 100 micrometer. So, that for that kind of size, the Knudsen number is not important for liquids. For gases, Knudsen number has some relevance. In fact, it is of the order of micrometer. So, for gases you need to consider the Knudsen number. Now, when it comes to the mixing, generally the mixing we refer to the mixing of liquids, because mixing of gases is much easier, because diffusivity of gases would be much higher. Okay, so, mixing we are referring to is a mixing of liquids. So, here in this context Knudsen number is not important. So, these are some of the issues that we should have in mind. Now, when it comes to the definition of diffusion coefficient D, these are available in various handbooks, the diffusivity of various materials, but if I get into the theories of it, I see that there are two established theories which define diffusion coefficient for liquid and for gas. For gases, this goes by the name Chapman Enskog theory, and for liquids it is Stokes-Einstein law for liquid. All right. This you can refer any standard textbook on transport process. It need not have to be a microscale, because diffusion coefficient is a very general topic. So, transport phenomena by Bart Stewart Lightfoot, that would be just I mean, they have a very good discussion on this Chapman Enskog theory as well as the Stokes-Einstein law. Briefly, I point out what we have here in Stokes-Einstein law. Here we have the assumption here is about idealized slow movement of single rigid solute sphere through a continuum of solvent. So, while deriving this theory, they have assumed slow movement of single rigid solute sphere through a continuum of solvent. Through a continuum of solvent, a rigid solute sphere is moving, idealized slow movement. Okay. Net velocity of the sphere is proportional to force acting. That is what the assumption there is. For slow movement of sphere, Stokes' law describes the force, and there has to be a driving force here. I mean, you are treating the diffusing species as a rigid sphere, and that is moving through the continuum of solvent. What is the driving force? Where is the force? I mean, why it will move? The force is basically arising from chemical potential gradient. That is Einstein's proposal here. I mean, for a rigid sphere in a continuum, what would be the drag acting on it? That is already defined from fluid mechanics. Okay. Now, in case of a diffusing species, there wasn't any force. I mean, I am not pushing the molecule like a I mean, I am not using an external force to push the molecule. So, the driving force here is basically the chemical potential gradient, because diffusion happens because why a diffusion takes place, because of a concentration gradient, and mother of concentration gradient is probably the chemical potential gradient. Okay. And then this analysis can be extended for the first analysis was done for diluted solution, and then it can be extended to concentrated solution. If I write this Stokes' law here, the Stokes' law states that force is equal to 6 pi eta r 0 into V 1. Okay, what are these now? Pi is 3.14, eta is the viscosity of liquid, r 0 is the radius of diffusing species, and V 1 is the velocity. Okay. This is originally, this equation is available, this formula was available for a drag force. Suppose you have a rigid sphere, okay, and you have fluid flowing like this. The drag force exerted on the solid, that can be given by this formula, where V 1 is the velocity of the V 1 is the velocity of this sphere. So, the drag force is defined by this 6 pi eta r 0 V 1. Now, this has the proposal of the proposal here is that this is equated with the chemical potential gradient. Now, what is chemical potential for dilute solutions? Chemical potential is defined as some reference plus that same Boltzmann constant temperature and ln of x 1. X 1 is nothing but C 1 by C 1 plus C 2, where C 1 is equal to solute concentration and C 2 is equal to solvent concentration. Okay. So, when C 1 is much less than C 2, you can write grad of mu 1 is equal to, from this expression you can write kBT by C 1 grad of C 1. Okay. And the flux by in the context of mass transfer, the flux is equal to V1 into C1, solute concentration and the velocity of that solid of that rigid sphere. So, that is equal to V1 into C1. So, you can write this as minus kBT divided by 6 pi eta R0 grad of C1, because you are invoking this formula here. All right. So, flux can be defined as this, and you know what a flux definition of flux is. Flux is d into grad of C1. So, from these you can conclude that this could be the diffusivity of the liquid. Okay, so this is how I mean, if it is completely an unknown material, so for a dilute solution you can find the diffusivity. Now, for concentrated solution there are correction factors which are introduced. So, the analysis for dilute solution, that is the last point in the slide, can be extended to concentrated solution. So, if nothing is there in your hand, probably you can use a formula which already people have already the scientists and researchers they have already proposed. In case of gas, there is this Chapman Enskog theory, where diffusion coefficient is written as a function of temperature, pressure, molecular weight, collision diameter, Lennard Jones potential describing interaction of molecules. You can, as I said, you can refer Burt, Stewart and Lightfoot and find the exact formula there. I mean, I just here sitting here I can point out that you can find these diffusivity values in handbooks tabulated, or you can use some established theory. At least you can go close to that, if not exact, because the measurements are far more exact than these theories. These theories are based on certain assumptions, certain models. However, these could be handy if you do not have any place to start with. Okay, the next topic that I consider here in this discussion is the spreading of a spot in a resting fluid. See, I mean, the idea here is that we have to characterize this mixing. We should be able to theorize how this mixing will take place in a microchannel geometry if you introduce baffles, if you introduce more such artifacts in the microchannel. But first you need to understand how the diffusion takes place in a simple situation. Okay. So, we first try to find out what all equations we need to consider if we need to describe spreading of a spot in a resting fluid. Spreading of a spot in a resting fluid means this is a resting fluid, a beaker full of water, okay, and then you put a spot, a minuscule drop of a dye, ink, and then immediately you see the color diffusing into this resting fluid. How will you theorize this? What kind of theory will describe this spreading of color? Okay. So, a very small spot of tracer at t equal to 0 is expressed. How will you express a very small spot of tracer? Let us see intuitively what do we see. Intuitively, if we try to find out, suppose we are treating this as a one dimensional problem. So, if it is one dimensional problem, suppose this is Z, okay, and this is the concentration. You plot the concentration as a function of Z. So, at t equal to 0, what is the condition? At the beginning, it is a spot of tracer. So, spot of tracer, a very small spot of tracer at t equal to 0, that can be expressed using a Dirac function. The Dirac function is 0 everywhere except at the origin. So, origin is this point. So, to start with, you have a profile which looks like this. So, it is 0 everywhere except at the origin. Now, what the other thing that has to be satisfied here is that suppose you put, say, m is equal to the total amount of solute in the system. M is equal to total amount of solute in the system. Okay. Now, this total amount of solute in the system has to be conserved. By that what I mean is, if I look at, say, at higher time, at t equal to 0, I said it is 0 everywhere except at z is equal to 0, it has a finite, it has some value, and the integral of this area under this curve, I mean the area under this curve, that has to remain same, because as time progresses, how would be the profile? This is traveling all the way up, little higher time like this, some more higher at a further time instant it would be like this, right, and gradually it would be all flattened up. Now, the area under this curve, that should remain same, and that should correspond to the total amount of solute in the system. Now, whether you consider the Dirac, so the Dirac function has to take care of this aspect, that the area under this curve, even if you have a Dirac function, even if you have 0 everywhere except at the origin, the area under that curve as well has to correspond to this total amount of solute in the system. So, the area under the curve remains same, because you are not importing any solute from outside, that is that original spot which is spreading out. All right. So, the integral of the Dirac function is equal to 1, that is because that has to, otherwise you cannot satisfy this total amount of solute in the system. So, that has to be satisfied. Now, if you write the mass balance, on a differential volume, how would that be? You would be writing here, suppose you pick up at some distance z, you pick up a differential length dz, or say delta z, let us say delta z, let us develop this from scratch. So, you are picking up a distance delta z, all right. So, you would be, what you would be writing it, if you are drawing a mass balance there, you would be writing del t of A delta z C1, that is equal to A J1, that is the flux at z, minus the flux at z plus delta z. What is A? A is equal to cross sectional area over which diffusion occurs. All right. So, this is the mass balance on this differential element, and then if you write this as del C1 del T, then this would be equal to minus del Z of J1, which can be written as d del square C1 del Z square. So, this is the governing equation. I mean, you are already familiar with this governing equation. You must have seen this equation in the context of mass transfer. Only we revisit that and we ensure that for a spot of tracer that we arrive at this equation. Now, one thing you must understand, that this C1 would be written as C0 delta Z, that is equal to m by A delta Z. So, that is the condition at t is equal to 0, okay. And at t greater than 0, only thing we know is that at z is equal to infinity, C1 is equal to 0. That is the other condition we have. So, at t is equal to 0, concentration follows the Dirac function. That is the idea of Dirac function. And what is essentially, what does this mean? This means that integration between minus infinity to plus infinity. So, it is 0 everywhere except at the origin. So, what that means is C1 a dz, that would be equal to integration minus infinity to plus infinity m by a delta z a dz. Okay. And a cancels out, m comes out of the integral. So, a cancels out, m comes out of the integral. So, basically this is m integration minus infinity to plus infinity delta z dz, and I pointed out this, that the integral of this Dirac function is equal to 1. So, that is what I said, that it is this is equal to m into 1. So, this is basically m. So, this material this result is m, because this integral, the value of this integral is equal to 1. So, that is what probably I referred here in this slide as the integral of this Dirac function. Basically, I should have said from minus infinity to plus infinity. So, this is basically the condition that we have. So, one condition is at t equal to 0, we satisfy this part, that is what we have in hand. The other condition is at t greater than 0, z is equal to infinity, the C1 is equal to 0, because at z equal to infinity, that is far away from the spot, far away from the place where you put the spot of tracer, there is no effect. That is what you say here, the C1 is equal to 0. That means, the color cannot go all the way to the infinity, because after all you have put a very small spot of tracer. So, these are the two boundary conditions, and this is the governing equation. Now, this equation there is a solution existing. So, what we will do is we will I can give you the solution right away, so that you can get a I mean, when you go back, you keep this in mind how it looks, and probably in the next class we will briefly touch upon basically you need to use the Laplace transform to solve this equation. However, handling this Dirac function, handling this boundary condition will not be very straightforward. There is a trick to it. This particular boundary condition in Laplace transform, you try to do it after you go back after this class. You try to do it yourself. I give you the final form. The final form is m by a square root of 4 pi dt e to the power minus z square divided by 4 dt. This is the final form, z square, mind it, z square by 4 dt. This is the final form that we have. So, when you go back after this class, you try to see how it can be solved. In fact, in the next problem that we will pick up is where you do not have a spot of tracer, rather you have a front. Suppose you have a front, that means you have a concentration which is all the way here. So, your boundary condition would be different at that time. This would be at z is equal to 0, you have C1 as C1 0, that kind of boundary condition. There probably handling this boundary condition is much easier, but here it is not straightforward. What I suggest you do is you go back and try to solve this using Laplace transform. Okay, and next class we will probably spend first couple of minutes to find out what are the intermediate steps. Okay. So, thank you all, that is all for today.